Hi there, nice to see you again. This is a new Entanglement tutorial. Today, dealing with soft body spheres. But wait, although soft bodies are quite popular and you can easily achieve them with vellum in a simulated form, we want to do something different today. I want to show you how to create a fake soft body effect. So I want to use an analytical method to remove the intersections from spheres, basically. I want to pack the spheres and then do proper intersection removal, such that the spheres appear as if they were pressurized balloons. This has advantages, as it is faster, as you might expect. And you can use it without simulation at all, so you can just do a packing and use the operator on this packing. So I think it's sufficiently interesting to give it a try. So let's dive in and start. First, let's create a geometry node, call it Analytical Foam. That's the name that I came up with for this tutorial, and dive inside. Let's create a grid, like in most of the tutorials, and let's make this 0.5 by 0.5, like so, a small, tiny grid sitting here. And now let's create a packing by appending a scatter. Just a scatter with standard settings. Let's scatter 50 points, say, like so. And now let's place some spheres on these points. So create a sphere. And switch the sphere from primitive type primitive to polygon. And give it some frequency, say 8, to have something to work with. If we make this visible, you see I have a subdivided sphere. And now with the copy to points, I can copy the sphere over to my points. If I do that, I have large spheres covering my entire grid. So let's care about the pscale attribute first. To do this, I like to use wops, so create a point wop, and append it here between the scatter and the copy to points to affect the template points, and call it set pscale. Set pscale. And let's dive inside. So now, my standard method to vary pscale is to use an anti-aliased noise. So put down an anti-aliased noise. And you've seen this in so many tutorials now. The anti-aliased noise outputs values in the range between -0.5 and 0.5. That is why I append a fit to transform this range to 0.5 to 0 to 1, because now I can append a ramp parameter to remap the value range. Let's call this parameter ramp noise, and let's switch it to be a spline ramp. Okay, after the ramp I have values between 0 and 1, but the final pscale will be smaller, so append another fit range to be able to set the final values. And now let's bind this, bind export, to pscale. Pscale, like so. So this goes into here, and everything vanishes because pscale is set to 0 now with the standard settings. But before we dial in the settings, let's promote some parameters. First, we will need the frequency of the noise. The ramp noise automatically creates a parameter, and we want destination min and destination max from the second fit node, because these are the final values that we can dial in. Now that we have that, we have a nice interface here on our operator. The first problem is that the ramp is set to 0 entirely. So let's go up with the second value. And here we have our large spheres again. And then let's dial down the minimum and maximum values to something that we can work with, say 0.02 and 0.08, something like this. Not much variation here, because the noise frequency is not set correctly. So let's go in and just up the frequency until we have some variation. And we can make the effect stronger by giving some contrast to this ramp, like so. Okay, but now the big spheres are still a little big, so let's go down to 0.6 maybe. And let's increase the small radius, something like this. I just want some spheres that are intersecting and others should not be intersecting. So very nice. Now I have spheres that are intersecting, And what I want to do is I want to remove these intersections. So let's quickly think about what we want to achieve. We have spheres intersecting. If I turn on wireframe, you see I have points of this sphere inside of the other sphere, and I want to get rid of this. So my target is to find these points, then calculate the plane of intersection, so the plane where these two spheres are hitting each other, and then I want to just move all the points that are inside of the other sphere to this plane. If I do this to all spheres, I get rid of the intersections. And after that, I can just apply a smooth operation to give the impression of having balloons. But it's not that trivial, because here we only have one intersection, but we have a lot of cases, like over here, where we have many intersections. So this sphere, for example, is intersecting many other spheres. So we have to go over all the intersections. So the very first step will be to find the intersecting spheres. And you guessed it, we will do this using vex. So let's append a new wrangle, a new point wrangle. Let's put it here beneath set pscale, and let's call it gather data, because I want to gather the data first on the template points, and then later on, after the copy to points, I want to go over all the points and deform them using the data that I gather here. So this will be the first operator to implement. So let's press Alt-E over the code editor, and let's get started. The first thing is that we want to find all the spheres that are intersecting. There are several ways to do this in Houdini. psfind is one of them, and another one is to use the function nearPoints. To me, nearPoints is a little easier to use, that is why I use that. So let's create a new array, integer called neighbors, that will hold the indices of all the spheres that are intersecting, and then let's use the nearPoints expression, nearPoints, like so. And we want to search on geometry stream 0 around the point at P, and the radius to search in should be max dist, like so. So first we have to define this maximum distance to search. And think about it. The maximum distance that intersections can appear in is the largest sphere of our entire set times 2. So if both spheres are of the largest kind, then we will exactly have this distance between them. So let's just use the higher pscale value that we used in the operator before and double it to have max dist. And I can do this by first creating a parameter. So let's type float max dist, and that should be channel max dist, like so. Apply, accept, press this little button, and here we have our max dist parameter. Now go to set pscale, copy the higher value, copy parameter, and go down here and say paste relative references. So now it's referencing whatever we dial in here as the maximum size of the particles. So we said we want to double it, so let's say max dist times 2. Now we have an array of all the neighbors of the spheres that are probably intersecting, but not necessarily. If we have the case like here, and we search in a radius around this sphere, for example, with max dist times 2, we find all of these spheres, but they are not intersecting. So we have to do a second test if they are really intersecting. This is only giving us the local neighborhood of our point. And before this, let's quickly bind the results to an array. So I brackets at debug is neighbors to look at our results. Apply, accept, go to the geometry spreadsheet, and here we have our neighbors that have been found. And you see, the very first entry in this array is always the point itself, so we have to get rid of the very first point. So let's do that by using a pop operation. So let's just write after the array creation pop, and then neighbors, and we want to remove index 0. Easy as that. Apply, accept. And now the first entry is gone from the array. So we eliminated ourselves, so to speak. Great. Now that we have that, let's get rid of this debug, not necessary anymore, and let's introduce our second test. For this, let's run over all the found neighbors. So let's do a for each loop, for each integer neighbor, let's say. You can call this anything, but I call it neighbor because that is what it is. And it should be inside of the array neighbors, like so. And then curly brackets. So everything will be executed for each individual neighbor. And now we want to do some math, because the spheres are really intersecting if the distance between them is smaller than the addition or the sum of their pscale values. So if I take the pscale value of this sphere and this sphere and add them together, then I have the distance that they have to be apart to not intersect. And if the real distance between them is smaller than that, then they are intersecting. So let's calculate the data that we need. So first we have to gather some information about the neighbor that we are working with. So first will be float, I call it n pscale. That is the pscale of the neighbor that we are currently processing. And we use a point function to get it, 0 pscale and neighbor is the index. And then we will need the position, because we have to calculate the distance between the neighbor and the currently processed point. So vector np will be the neighbor's position. Another point expression or point function. 0 p is the attribute and neighbor is the index. Now we have the necessary information. Let's use it. First, let's create the vector between the 2 points. So a new vector. I call it between, and it should be n underscore p, which is the position of the neighboring point, and our position at p. So that is a vector between the two. But we need the length of this vector because we want to find the distance between the 2 points. So let's create a new float, call it dist. And let's just calculate the length of the found vector between, like so. And then we want to have the clear distance, so the distance that they are apart when they are not touching. So float clear will be n pscale, so the pscale value of the neighboring particle, and not semicolon here, but plus our own pscale. Okay, now we have all the necessary information, and we can now write our if clause. So if the distance between the particles is smaller than the clear distance, clear, then they collide. Great. And for now, let's just mark this with attribute. So let's quickly introduce integer collided. Set it to 0, and let's just add to this collided variable in the case that they are intersecting. And now after the end of the loop, let's just bind this to I at collided. This should be collided, like so. This is just for testing. Apply, and we have some errors here. Let's quickly see what went wrong. Apply. I have a typo here in length, like so. Apply, and now it's working. Let's see if we have an attribute collided, and we have one. Counting the collisions, how many collisions there are. Maybe it might be beneficial to visualize it. So let's create a new visualizer, call it collided. It should visualize the collided attribute. And this is a little convoluted, so let's make gather data visible and just template this, and now we can see if this is counting correctly. So here we have a 3, it's colliding with 3 spheres. these all are colliding with one sphere, so the value is 1. That has a 4. Seems as if this is working. This has a 7. 1, 2, 3, 4, 5, 6, 7. That's true. So it's working. It's counting how many collisions we have, and that means that the check is working. So the code here, collider++, is only executed if the spheres are really colliding. Now that we have the colliding spheres, we have to calculate some stuff. We have to calculate the distance from the center of the sphere that the plane of intersection lives. So if you look at these two spheres, for example, here we have the plane of intersection. And it's further apart from 4 than it is from the center of 2. And we have to somehow calculate this. So I looked it up on the internet, to be honest. I just went to the good old website of Paul Burg. And this helped me in the past, and it helps me this time, because he has an article here on intersection of two circles, and that is basically what we need. So if we have two circles, you see the distance from P0, that is the center of the first circle, to the intersection plane is A, and the distance from P1 is B. And using the Pythagorean theorem, we can find these distances if we have the radius 0 and the radius 1. And Paul did all the math for us, so here's the formula that we need. A, which is the distance here to the intersection plane, is the first radius, in our case this is pscale, squared minus the second radius squared, which is pscale of the neighbor, plus the distance between both of them squared, and all of this divided by 2 times the distance between them. So let's just implement this formula inside of Houdini. So inside of this if statement, let's write float my sect dist is, and now let's just implement the formula that we saw a second ago. First we want to square pscale, so power at pscale 2, that squares pscale, minus the neighboring pscale, so again power, and then n pscale 2, plus the distance squared, so plus power dist 2, and all of this divided by 2 times the distance, so 2 times dist, like so. And that gives the distance to the intersection plane as seen from ourselves, so from the point that is currently processed. But be careful, we are still inside of the for each loop, so chances are that we have more than one intersection and more than one my sect dist. And we somehow have to keep track of all of them. So let's create an array and append the result from this calculation to the array. So up here, let's create a float array, float, and let's call it sect dist, and it is an array, just like that. So with this in place, we can write append, and then the array, which is sect dist, and we want to append my sect dist, like so. And now we save all of the values to this array. And we want to use this later on, so we have to bind it to an attribute. And we can do so by just stating f and then brackets to indicate that this is an array attribute. And let's just call it sect dist. And it should be sect dist, the array. Apply, accept, quickly check if we have it. Here is sect dist. And you see collided is 1, and we have one sect dist value, collided is 0, we have no sect dist value. This is working. Great. And then we want to move the points. So now we have the distance from the center of the sphere. And it's simple. We just have to see if the points are further away from the center than sect dist. And if so, we just have to move them back to sect dist. But the problem is that sect dist is just a float. This only works in the direction of the line connecting the two neighbors. So we somehow have to rotate all the points such that they are pointing in the direction of the neighbor. If we do that, if we, so to speak, localize all the points of this sphere, we can easily check if the z component of all these points is bigger than sectdist, and if it is, we can just clamp it to be sectdist. And this will have the effect of moving all the points to the plane. To do that, we need a matrix though. So we want to create a matrix that has its z-axis oriented along this line that is connecting both. And then we can use this matrix to transform the sphere temporarily to a local space where we do the calculations. So let's quickly do that. If you watched my polyfolding tutorial, you are familiar with matrices. So I will go over this quickly. So first, let's create all the vectors that we need. The first vector will be the z-axis. Vector, z-axis. And this will just be the normalized version, because we are targeting an orthonormal matrix, the normalized version of between. Remember, that is a vector connecting our point with the neighboring point. Then we want to create a temporary vector, call it TMP, to be able to do the double cross product technique and just cross this z-axis with global y. 0, 1, 0. That is global y. And just in case, let's normalize all of this because it's necessary that this is normalized. Normalize cross z-axis with global y. Now we have a temporary vector that is perpendicular to the z-axis. Now we can calculate the y-axis, and that will be the cross product of the z-axis with this temp vector. And now that we have a z-axis and a y-axis, it's easy to create an x-axis from it. Vector x-axis will just be the cross product of z-axis and y-axis, like so. And with all of these axes in place, we can create a matrix. So let's create a matrix, call it my xform, and let's set it to be composed of the four vectors x-axis, y-axis, z-axis, and add p. Because we want to center the matrix around the point itself, as we intend to localize all the points of the sphere that is copied to this point, like so. And because we are working in homogeneous coordinates, we have to correct for the fourth component of the vectors. My xform xa is 0, my xform ya is 0, my xform za is 0. If you don't understand this, watch my polyfolding tutorial. There I explain it. If you're not interested in the inner workings, this is just necessary to make the 4x4 matrix work. Great. So now we have a transformation matrix that can be used to localize our sphere and to calculate if the points are further away from the center than sectdist. But again, as we have many intersections, we need to store these matrices somewhere. So go up here and create a new array. This time of type matrix. Matrix xform, let's call it, and this will just be an empty array, like so. And now that we have this array, we can just append to the array xform our my xform, like so. And now that we appended this, we can create a new attribute of type matrix4 array, and that will be xform, and it should resemble our local array xform, like so. Let's see if we have some mistakes here. Doesn't seem to be the case, so let's see. Here's our array sectdist, and after that we have our array xform containing the entire 4x4 matrix for all the intersections. So we have one 4x4 matrix here at the top. Not possible to make this bigger, probably. We have one here, and we have multiple matrices down here. And if we don't have an intersection, we don't have a sectdist, and we don't have an xform. So this gathered data node gathers data for all the intersections of every template point and stores this localizing matrix and the section distance to an attribute array, and that can be used later on to transform all the points. Now that we have all the necessary information, we can implement the deformer. Very good. Finally. So after the copy to points, let's place a new wrangle. And let's call it deform. Because this should run over all the points that there are, not only the template points. So connect it here, but it will need the data gathered here in this node, so connect this node to the second input of the deform and make the deform visible. Let's turn off the visualization. Maybe switch to wireframe to see if this is working. And let's press Alt-E. So now we are running over all the points that we have. And the first thing we want to have is for each individual point, I want to know the sect dist of all its neighbors that it's colliding with. And I want to know the matrix that I have to use to do the local X-form. So the first thing I want to look up is the template point that created these points here. And I cannot do that. So let's quickly close this and let's add one line to this wrangle up here. And that is just I at ID is at ptnum. By doing so, we are writing the point number of the template points to an ID attribute. Quickly check, and here's the ID attribute. It's just exactly the same number as the point number. By doing so, the copy to points copies this over. So after the copy to points, we have this ID attribute on every single point. And this can be used to look up the template point that created the sphere point. So now with this in place, we can write float. So now with this in place, we can write float sect dist array and then just read it from the template point. So let's use a point function, but this time on geometry stream 1, where the template points are coming in. Let's read sect dist, and the ID is at ID. So for each individual point, it is looking up the ID that created this point in the first place, and then looks at this template point and reads the entire sect dist array from there. And let's repeat this for the matrix array. So matrix X-form, let's call it X-forms, and sect dists maybe because it's an array like so. And this will be point 1 X-form like so, and again at ID. So by doing this, we now have all the data in array form again. And now we can run just over the matrix array, say, because it has as many components as we have intersections, and then do our point calculations and move the points. So another for each loop is needed. For each matrix X-form inside of the array X-forms with an S, like so. Oh, I may have a typo here. X-forms. So now with this in place, the first thing is to localize the points. And for this, we need the inverse of the matrix. Because remember, the matrix is telling where the global position of the template point is with respect to the origin of the world. And now we want to move all the points to the origin of the world, so to local space, so to speak, and rotate them such that they are pointing in the direction of the neighbor to be able to do our measurements with the z-axis. And for this, we need an inverted matrix. So matrix X-form inverted is invert X-form. Oh, and I have a second typo here. Sorry for that. X-form, like so. Now we have an inverted version of the matrix. And now we can temporarily localize the points by just writing vector local p should be the current global p times xform inverted. And here's the third typo. I really have difficulties typing xform. Sorry for that. Like so. So local p is not moving the points in global space. It's just a variable, so it's just in memory, but we can use it to do our calculations. So let's do that. We want to move the points if their z component is larger than their sec dist, because then they're intersecting. So let's write if local p z component is bigger. And now we want to find the sect dist that is related to the matrix we are currently using. So we have to understand the iteration of the loop we are in. Because with a for each loop, you just get the xform that is currently processed, but you don't get an iteration. And what we want to write is we want to access the sect dists array like so, and then we want to use the component operator to target the sect dist that is at the same spot in the array as the matrix. And to do this, we need an index. The easiest way to do this is to use a different form of for each loop, one that counts the iterations. So if we just write int I here in front of matrix, like so, and then semicolon, we get the iteration of the loop, although it's running over the array. And that can be used to find the correct value from the sect dists array, like so. So if local pz is bigger than the sect dist of this collision, then we want to do stuff. And what do we want to do? Well, we want to move the z component, or we want to replace the z component that is bigger than sect dist to sect dist. So let's say local p should be, the x component shouldn't change, so that will be local p x. Same with the y component, local py. That just remains the same. But for the z component, we want to use sect dists. So let's read the value from the array. And that means if the z component of the point is bigger than sect dist, then move it back to sect dist. That is our new local point. But this is still in local space. To use it for the global space, we need to multiply it with the transform again. So now we can directly set at p the global position, and that should be the local p that we changed, and then just times xform. Form, like so. Okay, let's see if this works, and we have an error here, because I'm just not able to write xform. Form, xform, 2 m's. So another test. Accept, and let's see if this actually moves the points. Oh, I have the template on, and if I get rid of the template of copy to points, I was really anxious that this is not working, and it is working. You see, now the intersections are gone. Now all the points are moved back to the plane in local space and then transformed back to their original place and orientation. So before and after, before and after. And if I switch this to shaded again, you see now, no matter how often they intersect, they are just conforming to each other, like so. And as a last step, to make this a little bit more beautiful, we can just append an attribute blur. And this attribute blur should work on P, and it will just blur it out a little bit to make it look more balloon-like, as you can see. And here we have the effect. So now we created an analytical system that will remove the intersections and conform the spheres to each other. And if we go in to set pscale and change the pscale, you see, as soon as stuff is intersecting, or if I move this value, as soon as stuff is intersecting, it is conforming. And the very last thing to do is to save some memory, because here in deform we are reading the arrays from the template points. But the copy to points copies all this information over to all of the points, which wastes a lot of memory. So let's go to the copy to points and let's just go into these attributes here and let's just remove, by using this little hat symbol here, xform, and let's remove sect dist, like so. Let's see if this works. Yes, and they are gone, so no attributes anymore. So that means that these values are only saved to the template points here and not copied to all of the points, because we might get a lot of points, and if we have a lot of intersections, these matrices are using a lot of memory. So this gives sort of the Voronoi diagram, as you can see, but only sort of. A, we have gaps here, and B, where we don't have intersections, we keep the spheres. So it's very different to a Voronoi diagram, in a sense. And it can be used to model foam, because this is how foam behaves. And if you want to create realistic foam, of course you want to use some particles in the gaps and maybe don't use the attribute blur. But for this abstracted foam, that is what I decided to do. So I hope you enjoyed this video. I hope you learned something, and see you next time.
And now it's time to really thank all our patrons, especially PU Online Learning, Important Looking Pirates, Kyoko Sakane, Derek A. Johnson, Nick, Chris Ever, Rafik Anadol, Rob Bryant Jr., and Mohammed Al-Abri. Thank you so much for your continued support. Without you, this all wouldn't be possible. Thanks.